A meter stick is held vertically with one end on the floor and is allowed to fall. The speed of the other end when it hits the floor is assuming that the end at the floor does not slip. So we are going to find the speed of the other end. To find the speed of the other end of the stick when it hits the floor, we can use the principles of conservation of energy. This is a key concept, conservation of energy. Energy cannot be created nor be destroyed, but can change from one form to another form. Here is the ground or the floor, a reference point, and the total length of the stick assume as L. So the uniform meter stick and its center of mass will be at the middle point. Total mass seems to act at this point. So here is the center of mass. So the potential energy will be act at the middle point. So L by 2. So mass of the stick assume as M. This is L is the length of the stick. And now we are using the conservation of energy. When the stick is vertical, it has the potential energy. When the stick is vertical, it has the potential energy and no kinetic energy, because there is no speed, so there is no kinetic energy. As it falls, potential energy converted to rotational kinetic energy. So the stored potential energy is converted to rotational kinetic energy. That is what I said. The conservation of energy is applicable here. The initial potential energy of the stick relative to the horizontal portion of the floor is mgh. Here the height is from the ground to the middle is L by 2. So this is the equation for the potential energy. Now when the stick hits the floor, now this end of the stick hits the floor, all of this potential energy will have been converted into rotational kinetic energy. Okay, this much potential energy is converted to rotational kinetic energy. So we are writing the formula for the rotational kinetic energy, half I omega square is same like the linear kinetic energy, half m v square. In the rotational the mass change to inertia, moment of inertia, and the velocity is converted to angular velocity omega. Okay, now here we are going to derive the formula more. As we know, I is the moment of inertia of the stick about the pivot point. This is the pivot point, the ground point, and omega is the angular velocity, and here is moment of inertia. Okay, now I is equal to 1 by 3 ml square. This is the moment of inertia of the uniform rod. This is the uniform rod. About one end is given by about one end. This is the pivot point. So about the one end is given by this formula. Now we are going to set up the conservation of equation. What are we going to set up? As I told, potential energy is equal to rotational kinetic energy, and write the potential energy formula, that is mg L by 2, and rotational kinetic energy is half I. The moment of inertia is 1 by 3 ml square multiplied by omega square. Okay, you can simplify this. Here is 1 by 6, then mass is cancelled, length, here one length is cancelled, and here 2 cancelled. So you can write 1 by 3 L omega square, the other side is G. Okay, you can take this 3 the other side, 3G, and L to the other side denominator is equal to omega square. Now omega is equal to, take the square root both sides, 3G over L. Now we are going to find the speed at the other end, the linear speed. Now we find the angular velocity. There is a formula for finding linear speed. V is equal to omega multiplied by the length. So write length here and then fuse the value of omega, 3G over L. When you take L inside, it becomes L square over L. L cancel. Answer is 3GL. So this is the formula to find the speed, the linear speed, when the ruler hits the ground. Okay. Now we can apply the values. Sometime this would be the option. Sometime the values will be given. So values are 3 times 10 times the meter ruler length. So it is a 1 meter, square root 30 meter per second. Thank you.